Cool. So yeah, I'm fairly confident that you could find exceptions to that. But I would say as the general trend, yes, that's true. The stronger the intermolecular forces, the higher the density.
Awesome, thanks.
Yeah. Other questions about this? Cool. So there's some properties that arise because of the strength in intermolecular forces, specifically those in things that have hydrogen bonding. So one of those properties is called surface tension. So this is a property in liquids that results from the tendencies of liquids to minimize their surface areas. So we live in a place that has gravity, so when we see droplets, they don't appear spherical, but you guys can imagine that in the absence of gravity, they form perfect spheres, right? Does that make sense?
Yeah.
That formation of a sphere happens because the molecules that are at the surface of the water behave differently than the ones in the interior. And that's because of these cohesive forces. So the molecules stick together in the center and actually pull on the molecules at the surface, because the surface molecules don't have any other molecules interacting with them on that top layer, right? So the net pull is from the center of the liquid on that that outer layer of molecules, right? And that's what forms that spherical property. And that's also what allows for this surface tension, which can support the weight of a paperclip if you've never done that before. It also makes this convex surface on the top of a liquid, a glass of water that's been overfilled. So, questions about surface tension? Puppy.
Can you hear my dog drinking?
Super cute.
He's so loud.
I love it. Cool. So this gives you kind of an example of, or a better picture for what we're talking about with this surface tension, right? So the molecule that's sitting up top here is only being pulled on by molecules that are beneath it, right? Whereas this molecule in the center is being pulled on by all directions. Does that make sense? So that's what causes this tension at the surface. You guys cool with me?
Yeah.
Cool. Okay, so another property that arises from the strength of intermolecular forces is called viscosity. Viscosity is defined as the resistance of a liquid to flow. It's measured in the cutest of units, which is poise. So 1 poise is equal to 1 gram per centimeter per second. Often measured in centipoise. Oh, so cute. So larger intermolecular attractions mean higher viscosity. The stronger the intermolecular forces, the higher the liquid's viscosity will be. So I don't know if you guys, it's been a million years since we've been in lab, but have you guys ever tried to pipette a liquid that isn't water?
No.
Anybody?
Yeah.
Like a different liquid?
Yeah.
Yeah.
So what happens when you try and pipette different liquids?
We usually have to like put a little bit and then like mix it around. Is that what you're talking about?
Dilute it usually.
I think you're thinking about trying to clean out the instrument, but I'm thinking more in terms of how well the pipette holds onto the liquid.
Well, depending on the liquid, sometimes it takes longer for it to come out, so you have to dilute it.
Yeah, so if you have something that's really oily or really thick, it's going to have a high viscosity. Those high viscosity liquids are going to be harder to get out of the pipette. They're going to take longer. Really low viscosity liquids are actually really hard to keep in a pipette. So I don't know if you guys have ever tried to pipette alcohols. but they tend to want to fall out the bottom as you're transferring them. So that's something you guys will see eventually. Those are lower viscosity molecules. So that's one way that you can kind of think about the viscosity. More spherical molecules will be lower viscosity, right? So these really, really big organic molecules, even though they have only dispersion forces, their contact to contact is going to be create stronger intermolecular forces or induced dipoles, which is going to make them roll less easily, which is going to make them more viscous, right? Raising the temperature of a liquid also reduces its viscosity. So basically, if you're giving the molecules more energy, then they're going to be able to move faster, right? So their viscosity will be lower. Does that make sense, guys?
Yeah.
Cool. Any questions about these? So you should know the general definitions of both surface tension and viscosity, right? So looking at different oil grades, this is not the best picture in the world, right? But these lower grade oils are much less viscous than some of the higher grade oils. And the higher grade oils are going to be better at making sure that your pistons are moving at the appropriate speeds to make sure that, you know, your engine isn't catching on fire or whatever. I'm clearly a mechanic, you guys can tell, huh? Questions about viscosity? Easy peasy? You guys heard that term in general parlance? Viscosity?
I think so.
When do you hear viscosity mentioned? Or what's a context in which you've heard viscosity mentioned? No. You guys don't want to play with me today? Anybody? So before I learned about viscosity in the chemistry sense, I learned about viscosity in terms of lava flow. You guys ever heard that?
Yes.
So higher viscosity means lower lava flow. Lower viscosity means higher flow. All right, so another example of where these intermolecular forces become important is capillary action. So where are capillary actions important?
In the heart. Like,
in the heart, specifically in your blood veins, right? What else? I want to make you guys talk to me.
What was the question?
Where else is capillary action important in nature?
Pipes?
Pipes, not so much, because pipes are pretty big. Thinking more in terms of nature.
Plant?
Plants, yes, right? So plants are particularly dependent on capillary forces, right? So they have these tiny little arteries that go from their root systems all the way up the plant that are able to deliver water to places higher up in the plant, right? Without capillary action, plants would not get very tall, right? So capillary actions is the ability of a liquid flow against the force of gravity in a thin tube. The narrower the tube, the higher the liquid is able to rise. So there's two forces working in conjunction to make capillary action happen. The first is cohesive. So the cohesive forces are the ones that hold the molecules together. So this is the molecules holding on to each other. And then the adhesive forces. So adhesive forces attract the outer liquid molecules to the surface's tube. So capillary action happens because the smaller the tube is, the more the adhesive quality starts to dominate the behavior, right? The cohesive forces are still pulling on the interior liquid, right? But the thinner the tube is, the more adhesive interactions there are and the less cohesive interactions there are. Does that make sense, guys?
So this has nothing to do with viscosity, because I'm trying to picture, I know like when you decrease the size of the tube, would that still reduce the flow?
So when we're talking about viscosity, we're talking about the natural flow. So this is in the presence of gravity, right? And we're not talking about any adhesion or any container. Does that make sense?
So
So
in
we're talking about capillary.
capillaries.
Go ahead.
Oh, sorry. So I was just trying to like, because I understand why the liquid would rise, because if you have like a smaller tube, then more liquid is going to push up. But you're saying that the reason for that is because of these forces?
Yeah, so basically what we're saying is specifically in terms of the types of containers that we're usually holding liquids with, a lot of the times it's glass, which is a type of silicate. So glass tends to have a lot of oxygens, which are very into bonding with hydrogens in the water, right? Not bonding, hydrogen bonding. And so basically what you have is the water molecules are climbing up the side of the container, right? By these attractions to the container, the adhesive attractions. Does that make sense?
Yeah, that clarifies it a lot.
Yeah. So, and that's not always the case. So not all liquids have that kind of adhesive property, right? Water tends to be really good at capillary action because it's so polar, right? But other liquids that are less polar would have much less capillary action, right?
Okay, that makes sense.
Questions about that? So the other thing that these capillary forces lead to is menisci, right? So you guys know when you're looking at a liquid in a glass tube, you get this concave meniscus forming, and that's because of the attraction from the water molecules to the glass container, right? This is a better picture of what I was just describing, Angelique, but that's what we're talking about. Right?
I see. Yeah, no, that makes sense. So
yeah.
One we're assuming is in a container and the other one's not. That's the biggest difference.
Essentially, yeah. So one is looking at the liquid just by itself, and the capillary action is looking at the liquid and the container relationship, right? Okay. But like we were saying, water molecule is especially polar, so its interactions with a container, especially a container made of glass, are going to be really strong. Whereas you see mercury, which is not something we get to work with very often, but it has a convex meniscus. And that's because of the fact that the mercury molecules the mercury atoms are not at all attracted to the glass, right? In fact, they're slightly repelled. So these metallic bonds are stronger, meaning the cohesion between the metal atoms is much stronger than the intermolecular attraction between the liquid and the container. Does that make sense? So I'm trying to think, there's not a lot of other substances that have this property of having convexed menisci, and I can't think of another one off the top of my head. So it's not super common. This is a more common state, but it can happen, right? Where you can see the cohesive forces are outweighing the adhesive forces. Questions? Cool. All right. So this is kind of just talking about what we were talking about before. So gases are very sensitive to changes in volume and pressure and temperature. Compressing a gas, making it be under high pressure, or reducing the temperature can force a gas to condense or form a liquid. The volume of the container, if the volume of the container is increased, the molecules in the gas will expand to fill the container. A liquid with very little IMF will be more, you guys know what I mean by IMF, intermolecular forces? You okay with that? Will be more volatile. More volatility means that more of the molecules are able to escape to the gas phase, right? So thinking about our example of ethanol and water, which one would be more volatile?
Ethanol?
Ethanol, absolutely, right? So ethanol is going to be easier to get to go into that gas phase. Phase changes are characterized by the breaking or forming of intermolecular bonds between molecules. So higher intermolecular forces between molecules or atom mean that they will resist phase change. Said another way, they require more energy to make those same phase changes, right? So this is kind of just a picture of the same thing that we just said. So molecules that are very close together, very dense, are not going to be affected very much, even by tremendous pressures, right? So high pressures won't affect the volume of liquids or solids very much, whereas high pressures will extremely affect gas, right? So gases can be condensed by decreasing temperature or increasing pressure. Basically, what you're talking about when you're talking about compressing a gas is you're talking about reducing the freedom of the molecules, which is exactly what you see in a liquid. Does that kind of make sense, guys?
Yeah.
Okay. So what we want to talk about now is phase transitions, okay? So we're looking at phase transitions. I think most of these terms are hopefully familiar with for you guys, but some of them might be a little bit weird and new. So going from a solid to a liquid is called melting, aka fusion. This is probably my least favorite named phase change in the entire world, because to me, the word fusion means sticking things together. And melting is the opposite of that. So I tend to always use melting and fusion together because I think the word fusion is a really bad misnomer. But you guys should know that fusion means melting, okay?
Yeah.
Cool. Going from a liquid to a solid is called freezing or crystallization. Going from a liquid to a gas is evaporation or vaporization. Going from a gas to a liquid is called condensation. Solid to a gas is called sublimation, and gas to a solid is called deposition. So those last two are probably some of the newer ones, especially the gas to a solid. So those are ones that you're probably going to have to think a little bit more about in terms of making sure that you understand those. Okay. So looking at this diagram, if we're starting at a solid and going to a liquid, right? What's happening to the molecule's freedom going from solid to liquid? Are they getting more or less free?
More free.
More free, right? So in order to get more free, what do you have to do to the molecules?
Increase the temperature.
Increase the temperature, aka give them energy. Does that make sense? You guys with me? Yeah? So if you have to give them energy to go from a solid to a liquid, is that endothermic or exothermic?
Endothermic?
Endothermic, absolutely. Does that make sense? So melting is endothermic. Everybody with me?
Yeah.
What about freezing? What's happening to the molecules when you freeze them in terms of the molecular freedom?
They're getting more squished together and compact.
Yeah, they're getting less freedom, right? So that means what had to happen to the molecules?
Release energy.
Yeah, you had to take away some of their energy, right? So when you take away energy, that is an exothermic process, right? Does that make sense?
Yeah.
Everybody all right with me on these? So what about vaporization? Endothermic, exothermic?
Endothermic.
Endothermic, right? You have to add energy to make that happen, right? The molecules are getting more freedom, so they need more energy to do that. What about sublimation?
Exothermic.
Exothermic?
Is it solid gas?
So sublimation going from a solid to a gas, what happens to the molecule's freedom?
Oh, it increases.
It increases, right? Which means that we must have added energy.
Okay.
I thought
So
you said condensation.
sublimation.
Oh, sublimation. Sorry.
Sorry.
I was like, we're going to order.
Sorry.
Okay, so sublimation.
I was trying to mix it up for you guys, yeah. So we go in order, they toggle back and forth, right? But yeah. But the idea that I'm trying to get you guys to think about is these concepts of phase changes and whether or not they're endothermic or exothermic are only intuitive if you think about what's happening to the motion of the particles. Does that make sense?
Yes.
Especially because what happens when a solid goes to a liquid, right, is the molecules, you're essentially undoing this, this solid process, right? And for whatever reason, this becomes really, really counterintuitive for students. They really want to say that solid to a liquid means that you're exothermic, right? But when you think about what's happening to the molecular freedom, I think it's easier to see that you have to add energy to a solid to get it to form a liquid, right? Does that make sense, guys?
Yes.
Cool. So, okay. Question? No, cool. So if we have high energy molecules at the surface, they may have enough energy to overcome the attractive forces. Therefore, larger surface area, the larger the surface area, the faster the rate of evaporation, right? So if you have a bottle of water with a very narrow opening, the water is going to evaporate much more slowly than if you have it sitting out in a pan, right, where the surface area of the water is a lot greater. So this is my favorite. I love these GIFs showing what's happening with vaporization, right? So you have the water molecules. Again, we think about liquids and solids as being stationary, unmoving molecules, but they really are moving around, right? They're just not moving around as much as molecules in a gas, right? But you can always imagine that there's some of these molecules in a liquid that have enough energy to escape and become vaporized. Does that make sense, guys?
Yeah.
Cool. All right, so when we're looking at thermal distribution of energy, so if we have a lower temperature, then we have more molecules being centered right around that lower energy, right? but the energy distribution is always going to have different energies for different molecules, right? So when we were talking about gases, we said that the temperature is proportional to the average kinetic energy of the molecules, right? But not every molecule has the same kinetic energy. Does that make sense?
Yeah.
Cool. So if we have a lower temperature, it means that more of our molecules are going to be at a lower kinetic energy, right? But there's always going to be some that have enough kinetic energy to escape the surface of a liquid, right? So even at low temperatures, you still get vaporization occurring. Does that make sense?
Yes.
Cool.
So
Now,
it's not like all or nothing. It's like
exactly.
yeah. So
Exactly.
it's like if you apply more, you're gonna get more escaping, and if you apply less, okay.
Exactly. So what, and this is a really relevant kind of understanding of curvature right now, because this is the same concept as squishing the curve, right? So when we increase the temperature, what we're actually doing is we're flattening the curve of the kinetic energy of the particles, right? So we still have the majority of the molecules at this higher temperature are still below the threshold of energy to be able to escape the liquid. But we see that this tail end is now has more molecules than it did before, right? So more molecules at a higher temperature have that kinetic energy necessary to escape the surface of the liquid. Does that make sense, guys?
Yeah.
Cool. And you can imagine that if you kept squishing this curve down, right, the average would move until finally you get the majority of the particles coming over this kinetic energy barrier that they need to move into the next phase, right? Does that kind of make sense, guys? So
Yeah.
high temperature, faster rate of evaporation, right? Even if we're not talking about the boiling point, right? We're talking about all of the molecules being at that temperature, there's always going to be a distribution of energy in the liquid that allows for some molecules to escape to the vapor phase. So higher temperature and more surface area are the things that will increase the rate of vaporization. Beep, beep, beep. So going backwards from that, when you're talking about condensation, so vapor molecules are always going to have interactions with the container. Remember we said when we were talking about gases, we said that they don't have as many interactions with each other as they do with the container, right? So it's much more common for molecules in the vapor state to interact with their container, and those molecular collisions will make them lose energy. If they lose enough energy, then they can be recaptured by the liquid, right? If they're recaptured by the liquid, then this is the process that we call condensation, right? Yay.
Oh my god.
All the animals, Teddy.
I know.
Does that make sense, guys?
Yeah.
So one of the things that's really important that I want to make sure that you guys understand here is that these processes of evaporation and condensation are opposite processes, right? So they are bidirectional and they're always both happening. So it's not like evaporation always happens in that direction. It's always an equilibrium between condensation and evaporation, right? Whichever one is winning that battle, as it were, is the net change that we see, right? So does that kind of make sense?
Yeah.
Cool. So they're opposite processes. They the one direction requires energy input and the other direction is giving off energy, right? So condensation is the loss of energy, meaning it's exothermic, right? Evaporation is endothermic because it requires the molecules to gain energy. Does that make sense?
Yes.
Cool. Cool, and then that's exactly what I just said, blah, blah, blah. So the net result in a closed container is that you find this equilibrium is reached where you have X number of molecules that are in the vapor state and X number that are being condensed, right? So in an open container, you can imagine that these processes of vaporization could continue until the liquid is completely evaporated, right? Theoretically. But in a closed container, that vaporization can only continue up to a certain point, right? And then condensation or collisions between the container and the liquid will start to reduce the amount of vapor, right? And so what you get is this steady state where it looks like there's no vapor being formed and no condensation happening, right? But they're actually just happening at equal rates. Does that, you guys picking up what I'm laying down? No? We're good?
Yeah.
Cool. All right, so the weaker the attractive forces among molecules, the less energy that's needed to vaporize them. The less energy that's needed to vaporize them basically means that more of those molecules will be able to attain the kinetic energy necessary to escape the liquid state, right? So liquids that evaporate easily, again, are called volatile. So you can think of gasoline, fingernail polish remover, aka acetone. And then liquids that do not evaporate easily are called non-volatile. So that would be things like motor oil. Water is somewhere in between, right? So when high energy molecules are lost from a liquid, it lowers the average kinetic energy. So if you're thinking about that curve where we said the molecules that have higher energy are able to escape, right? But every time one of those molecules escapes, it actually lowers the overall energy of the molecules that are left over, right? So if energy is not drawn back into the liquid, its temperature will decrease, which is why vaporization is an endothermic process. Condensation is exothermic, right? So you can imagine that in the absence of some heat, right, in the surroundings, which will add energy back into this system, that eventually this vaporization would have to stop because the energy of the molecules would get lower and lower and lower, right, until you got to some critical point where you couldn't evaporate anymore, right? But what actually happens in real life is you set up this temperature exchange between the surroundings and the liquid, right? Which kind of keeps resetting the energy of the molecules. Does that make sense?
Yeah.
Cool. Questions? We're okay? Cool. So remember our old friend enthalpy? So we're coming back to the chapter 6 days. So the amount of energy required to vaporize 1 mole of a liquid is called the heat of vaporization, aka the enthalpy of vaporization. Vaporization is always endothermic, therefore the delta H of vaporization is always positive, right? Condensation is exothermic, so it's equal and opposite to the enthalpy of vaporization. Does that make sense, guys? You guys picking up what I'm laying down here?
Yeah.
Cool. So what does it mean to have a higher delta H of vaporization? Are you more or less volatile?
To have a higher rate of vaporization, you said?
So if you have a higher enthalpy of vaporization, what does that mean in terms of volatility?
More volatile.
Hi, Bug. You guys want to say hi to my daughter?
Hi, cutie.
Sorry, I distracted from the question. Delta H of vaporization, if it's
is it more
higher,
volatile?
more or less volatile?
More.
More.
It's actually the opposite,
Oh.
right? So the higher the delta H of vaporization, that's saying it takes more energy to get those molecules to separate, right? More energy to separate the molecules is because there's more intermolecular forces between the molecules, meaning less volatile. Does that make sense? And you can see that in the table here, right? So rubbing alcohol has a lower enthalpy of vaporization than water. Acetone, which is nail polish remover, is even more volatile. Diethyl ether is even more volatile, right? So the lower this number is, the less energy it takes to get these molecules to go into the vapor phase. Does that make sense?
So volatile molecules, or I don't know if this is a general trend, but is it generally speaking that they are endothermic and increase movement?
So
Or things that can be volatile?
So all processes of vaporization are endothermic, right? But some are more endothermic than others.
Okay.
So higher enthalpy of vaporization means it takes more energy to make the molecules go into the vapor state, right? And the reason for that higher energy cost is because you have more intermolecular forces sticking the molecules together, right? So getting them to go into the vapor phase requires breaking apart all of those hydrogen bonds or whatever is holding them together. Does that kind of make sense?
Yeah, I'm just trying to see how, because I know with, okay, so liquids that evaporate easily would be liquids that have a less of an energy barrier.
Yes, and that less of an energy barrier is because they have less intermolecular forces.
Got it, okay.
Or less strong intermolecular forces.
Got it.
Yeah, this is a really, really important relationship to understand, guys. And I would say too, we haven't really talked much about how the material in chapter 10 and 11 compares to some of the previous chapters. But I would say that conceptually, there's a lot of moving parts in these chapters. And so making sure that you can accurately kind of diagram what's happening here is really, really important, right? Everybody with me in terms of the size of the delta H of vaporization and what it means about the volatility or the intermolecular forces in a liquid?
Yeah.
Cool. So this is kind of what we're talking about in terms of the rate of vaporization and condensation in a closed container, right? So if we put a little cap on our container, we get some molecules that are able to escape into the vapor state. And as more of them escape, you start getting a few of them condensing. And eventually what happens is you set up an equilibrium where the rate of evaporation and condensation are equal, right? So we have a steady state of the proportion of molecules that are in the vapor phase, right? And this is a energy diagram or rate diagram, excuse me. For the dynamic equilibrium process. I think I mentioned before, so we talked about a couple of other instances of dynamic equilibrium, but this concept of equilibrium is so freaking important in Chem 201, right? 4 out of the 8 chapters that you go over in Chem 201 are all about equilibrium and equilibria processes. So this concept of rates being equal without concentrations being equal is really important, okay? So what we're talking about is the rate of change, and the rate of change is essentially net zero when you reach this dynamic equilibrium. Does that make sense?
Yeah.
Cool. Mm-hmm. I think this is a good place for us to stop. So go ahead and